So this lesson, the actual calculations are mostly going to be based off the Pythagorean theorem and some basic right angle trigonometry. And mostly it's about a bit of problem solving about in terms of visualizing these angles in 3 dimensions when we're restricted to seeing things in front of us in 2 dimensions on a piece of paper or a screen or something. So here I have a 3-dimensional representation of this prism, and there's this right triangle kind of cutting through it. And we want to find the angle between the diagonals DB, which is here, and LB, which is here. So that angle we're trying to figure out is already labeled on here. That's angle beta, we can see here. And so to figure this angle, in general, I have a right triangle. Angle beta is part of a right triangle. And you can find the angle of any missing corner in a right triangle if you know 2 sides of the right triangle, its lengths, and then using trigonometry. In this case, I know right now just one side. I know the height of this triangle is 5 centimeters. I need to find one more length. And I can find the length across the bottom, this DB, by putting that on hold and looking at this right triangle on the bottom of this prism. Because if I look here, I have another right triangle. That is a height of 3 centimeters, a base of 8 centimeters, and the hypotenuse is what I'm trying to figure out. And so some basic Pythagorean theorem will solve this. And so I can say that side DB will equal the square root of 3 squared plus 8 squared, which ends up giving me root 73. And since I want to use this to go forwards, I'm going to leave it. I don't want to decimalize it, since this is actually exact right now. And so that length right here, root 73 centimeters, that's the distance from D to B. And so now I can actually find the measurement of angle beta or angle B that we're trying to find here. Because now I know that this is root 73. That is the base of my triangle. 5 centimeters is the height. And so from angle B, 5 is opposite to angle beta, and root 73 is adjacent to angle beta, so use the tangent ratio. And so a quick review using the tangent ratio here, I can say the tangent of beta is the same as opposite over adjacent, or 5 over root 73. With that said, though, I want to find beta, not the tan of beta. So what's going to be more helpful here is not actually to use the tangent function, but to use the inverse of tangent function. For example, I know what comes out of this tangent function. 5 over root 73 comes out. I don't know what goes in. Well, that's what inverses are for. And we reviewed inverses recently, so I'll say the inverse of tangent, or actually I'll write it like this. I can say that beta will be the same as the inverse of tangent at 5 over root 73. And while you've learned about inverses in a previous lesson, the inverse tangent function you've used in previous courses, and keep in mind again, all it's doing is switching around our inputs and outputs. For a standard right angle trigonometric function like sine, cosine, or tangent, what goes in is an angle, what comes out is this ratio. Well, we want this the other way around. For the inverse tangent function, what goes in is the ratio, and what comes out is the angle. And I want to think in degrees for the time being, and so make sure your calculator's in degree mode, and you should get approximately 30.3 degrees. All right, so here I have another 3-dimensional prism, and this time I have just a line, the segment from G to N shown, where N is the midpoint of AD. So if I look at this visual here, that N is halfway between A and D. So I know the distance from here to here is 4 units. So I want the angle between line GN, which you can see in orange, and the base, ABCD, the base of this. So here's the base of this. So the angle between that and that line in orange, that diagonal. Well, if I zoom in on here a bit, that angle I can visualize by drawing another right triangle here. And the angle we're really trying to find is this angle right here. That's the angle between the base, which I'll kind of draw in red a bit. Well, that's actually a bit too messy. Let's try something a little less messy here. So here's my base. So between that base and this line GN, the angle I'm really trying to find is what I have right there. And so a way I can write this is I'm trying to find angle BNG. So one option is I can say I'm trying to find angle BNG. The angle, if you just follow from vertice B to N to G, that is the angle we're trying to figure out. However, in IB, especially on examinations, quite often they don't use this notation that I just wrote down. So another way that is a little more common in IB examinations is we still say B and G, but we put this little symbol above the N to show that's the angle we're looking at. Because if you look at the visual there, what I've highlighted is right around the vertice of N there. All right, so how do I find that? Well, let's, again, zoom in here. To find that angle, I will, at some point, trigonometry will almost certainly be helpful. I know the height of this triangle here, this right triangle, that height is 4. And if I can just figure out one more side of this right triangle, I'm good. I'm going to aim to find the side from B to M, B to N, I should say. And I don't yet know what that is, but I can now put that on hold. And like the last question, I can focus on this other triangle I have right here. So if I look at that triangle, I have a 90-degree angle right here. So BN is a hypotenuse, and the distance from A to B I can see is 6. And so now I can find the hypotenuse of BN, or I can find the length of BN very quickly using the Pythagorean theorem. And so coming back here, I can say that BN will equal the square root of 6 squared plus 4 squared, which gives me the square root of 52. Again, I don't want to decimalize that. I want to use it going forwards. And now that root 52 is the distance of that line in black that connects B and N. So I'll label that right here. And now looking at this triangle that I've been looking at from the start, looking at this triangle right here, again, we have all these, if we're struggling with something, it's all these 3-dimensional visuals placed inside this 2-dimensional drawing. But now I know the height of this triangle is 4 centimeters, the base is root 52, and so that's all I need. And so I can find the angle using, again, the tangent rate function, or really the inverse tangent function. So I'm going to say here that angle BNG, or BNG, like this, angle BNG, is going to be the same as the inverse tan of, from that angle, the side opposite to it, which is 4, divided by the side adjacent to it, which is that root 52. And then you go to your calculator and you get approximately 29.0 degrees. And so once again, any challenges we may have are not so much with the calculations. See, there's not a lot of calculations here. The challenges are with how to get to the calculations, how to visualize all these slices inside a 3-dimensional object. That leads me to the last question. I have a square-based pyramid. Determine the measure of angle EBG, or again, on an IB examination, they would maybe call this EBG with like that. So again, this and this mean the same thing. The first one I'm more used to, but understand both and we're good. All right, so what is angle EBG? Well, that's the angle from E. Whoa, what happened there? That's the angle from E to B to G. So it's this angle right here. That angle right there. That's what I'm trying to figure out. All right, so now I know what I'm trying to figure out. I'll highlight that in yellow. That's angle EBG. How do I figure that out? Well, I've kind of drawn out this right triangle slicing through this square-based pyramid. I know the height of this triangle is 6 centimeters. So all I need is one more side. And so if I can find out the length of this side BG at the bottom, we're good. So how can we do this? Well, remember, this is a square-based pyramid, it says, which means if I focus on the bottom, on the square, and I draw this down here, I know this point in the middle must be exactly right in the middle, because it's a standard square-based pyramid. And so that means this must be a right angle, and this distance from here to here must be half of 10, which is 5, and the distance from here to here, from the midpoint to G, must also be 5. Otherwise, this wouldn't be a square. Now, I know the visual that was given doesn't look like a square, but it's actually quite rare that in an IB examination, the drawing is drawn to scale. So this drawing is not drawn to scale, but who cares? It says it's a square-based pyramid. And now I can see this triangle in the bottom. I can now use the Pythagorean theorem again to find that length from B to G. And so I'll say BG equals the square root of 5 squared plus 5 squared, which is root 50. And again, I'll leave it like that. Because again, that's not the value I really want. I want to, in itself, I want to use that to find this angle B here, or EBG. It's kind of a messy root 50 there. Let me fix that up. All right, and so again, to find angle EBG, I can use the inverse tangent of from angle EBG, what's opposite, which is 6, to what's adjacent, which is root 50. And again, that should bring us to about 40.3 degrees quite quickly on our calculator.